Welcome to the Adirondack Sky Center and Observatory. There's nothing more inspiring than the night skies in the Adirondacks. It just makes sense to start your visit to the wilderness above with us. Our current programs focus on immersive experiences for audiences of all ages. They reach as close as into our own community and as far away as students from around the globe. From inspiring presentations given by some of our friends as world experts, to our Keystone 4-day astrophotography conference, there's something for everyone, including live as well as virtual stargazing, customized programs for schools, and private events. In the case of the Adirondack Sky Center and Observatory, the sky is certainly not the limit, but only the beginning. A second building is currently in the planning stages in the form of an Astro Science Center and Planetarium. This 18,000 square foot building will be dedicated to the study of astronomy and space travel. The planned $15 million Astro Science Center will feature a state-of-the-art planetarium under a 30-foot dome, a 100-seat theater, and a large area for hands-on and interactive activities. Our many exhibits will include a Foucault pendulum, overhead models of the solar system, and historical permanent as well as traveling collections. It's our mission to make this an immersive experience for everyone. You will never be told to look and don't touch. This new building will be in addition to our existing roll-off roof observatory, which houses 4 permanently mounted telescopes. The final phase of construction includes a traditional observatory dome housing a new 22-inch research-grade telescope. Please contact us to become a member or make a donation to help build this new Astro Science Center and Planetarium and begin your journey to the wilderness above. And many of you know that we are in the middle of fundraising for our Astro Science Center with all of those wonderful features. I should mention that all of the images that you saw in that video of deep space objects were taken right at our roll-off roof observatory. So anyway, good evening and welcome back, everybody. This is the October installment of our Cygnus series presented by the Adirondack Sky Center and Observatory. My name is Seth McGowan and I'll be your host and moderator tonight. I am the Vice President of the Adirondack Sky Center and Observatory, and I'm sure you'll be enthralled by tonight's program. Before we begin, you'll notice that your microphones are muted. We'll have some Q&A after the presentation, and as always, we will post this video, which is being recorded currently on our YouTube channel, which you'll get the address for in a few minutes, but within a couple of days that this video will be posted there. So our presentation tonight, Ultima Thule and other subjects, and Ultima Thule, not the Viking band that you may have heard of, but something more deep space than even that. Our presenter, Mike Adler from Jackson Hole, Wyoming, is the Vice President of the Wyoming Stargazing. Mike graduated from MIT in 1971 as a PhD in the area of solid state physics and worked at General Electric from 1971 until his retirement in 2000. Since retirement, Mike has been active with the Institute of Electrical and Electronics and Engineers, the IEEE, which is the largest technical society in the world, including being its president in 2003. Mike's been giving talks on a number of topics in astronomy, geology, and travel to groups in New York and Jackson. In fact, Mike's been quite busy the past few days. I attended a talk he did last night at Paul Smith's, and he did another one earlier today. So he's been a busy guy. Hopefully we'll get to see some of his astrophotography, which is simply, no pun intended, out of this world. So with that, I welcome Mike Adler. Take it away, Mike.
Thank you, Seth. Appreciate that. Very happy to be here and with you folks. And we're going to immediately jump into this talk, which I hope you folks will find interesting. And I'm going to share my screen. And here we are. So we're going to start with the New Horizons mission that is still actually going on. But its goal originally was to do a flyby of Pluto. So I'm going to give you a brief overview of that mission first, and then we'll move on to the follow-on to that mission, which is Ultima Thule, and then to the Dawn and Rosetta space missions as well. Let's see. Okay. Yeah. So the New Horizons mission, it started in 2006, and 10 years and 3 billion miles later, it did a flyby of Pluto, and then another 3 years after that, it did a flyby of Ultima Thule, and so that's what we're going to be talking about. This is a picture of the spacecraft. It has quite a few instruments on it, quite a few cameras that photograph visible and other wavelengths. I think infrared. It also has a spectrograph, so it can measure compounds on the planet, and you'll see some results of that. This, just to give you a little snapshot of the outer part of our solar system, here we have the Kuiper belt, which is where Pluto is located. And so the first part, we're going to talk about the original main point of this mission, which was the flyby of Pluto. And then there was the subsequent flyby of Ultima Thule, which occurred in January 1st of 2019. Yeah, and I think you all probably know that Pluto was demoted into a dwarf planet from planet status, partly because there are other objects in the Kuiper belt and in the asteroid belt that are similar in size. And so some official body decided that Pluto is no longer one of our planets, and so it's been now demoted, but it's still it's an extremely interesting planet, as you'll see. So the spacecraft itself, as I mentioned, was launched originally in 2015, and it traveled and it did the pass flyby of Pluto. Actually, it was launched in 2006, and it did the flyby of Pluto in 2015, actually July 14th, and then flew 1 billion miles further in 3.5 years to reach Ultima Thule. It completed that flyby in 2019, as I mentioned, and it's still out there going along at something like 33,000 miles an hour. And so that, in fact, today, as of today, I got an update from the website. It is now 4.8 billion miles away from Earth. And that works out to be 0.0008 light years, which, or maybe in a little more interesting unit, 6.1 light hours away and traveling at 33,000 miles an hour. Now that sounds like it's a long way away, 4.8 billion miles after all, but to go to the nearest star other than the sun, at that speed, it would take 50,000 years. So we're not going to be going there anytime soon, as you can imagine. But to further put this in perspective, the most distant object Hubble has imaged is over 13 billion light years. So you can see that in spite of how far Pluto is, 0.008 light years, it's nowhere in terms of distance. You can get a perspective of how small our little solar system is, even though it seems big to us compared to the immensity of the universe. And so just going over the New Horizons mission a little bit, this was a image that was taken by the New Horizons spacecraft as it came close to Pluto, and it shows you these haze layers that exist above the planet. And then some of the, just a little more information about Pluto. It has a very significant axis of tilt, some ranging between 100 and 127 degrees, and it varies that over a 2.8 million year cycle. And its orbit is 280 Earth years around the sun. But due to the extreme tilting of the planet, our planet has a tilt of 23 degrees, while this is over 100. Because of that, most of the planet is in the polar area. So there's only a small area that's in constant light, and that's shown in this diagram here. And the temperatures in that band are not exactly warm, however. In this particular black area, the temperatures are up to about 43 K and Kelvin, and in the whiter area, it's even colder because it's reflecting some more sunlight, and it's about 37 K. But Pluto, because its orbit changes also, it varies between 2.8 billion miles and 4.6 billion miles. So it's not a circular orbit. So it sees a large variation in its temperatures and its climates. You all probably have seen this images like this before. This was one of the well, I don't call it surprises, but it was one of the main features that the New Horizons spacecraft uncovered when it was passing by Pluto. Realized it did not orbit Pluto. This was a flyby, and so this is this heart-shaped object, which is now been given the name of the Tombaugh Regio after Pluto's discoverer. It was first thought to be a raised area, but it actually is a depression that's about 3 to 4 kilometers deep, excuse me. And the actual cross section here is about 1,600 kilometers and about a temperature of about 38 K, as we just talked about. So this is a picture of at least one entire side of the planet that was done by the New Horizons spacecraft. And you can see there's some very interesting colors. These are real colors. This reddish color is made up of a substance called thiolins, which is comes from when UV light hits organic compounds or organic gas like methane. It creates these powdery compounds, and you'll see that this is also this same powder is in the Ultima Thule as well. Pluto rotates together with its largest moon, Charon, every 6.4 days. And during the flyby, it only saw, the New Horizons only saw one side of the planet, because by the time it rotated, it was long gone. So there was many surprises in the on Pluto that New Horizons discovered. It was far more interesting than the scientists originally thought it would be. For example, in the top chart or picture, it just shows the northern polar region, and you can see that it's quite, there's large areas that's very smooth, and there's evidence of movement. And the top surface here is mostly nitrogen ice, but it's not static. It actually moves slowly, albeit, but does move. The bottom picture shows this also a sea of nitrogen ice, but there are mountains sticking up to them. These are mountains that are quite high. They're 11,000 feet above the surface, and they have the name of Hillary and Norgay after the first climbers climbed Mount Everest in 1953. So a lot of interesting topology. Another of the interesting features is near the with the Sputnik Plantia, which is the right side of the of that heart-shaped object, are these interesting patterns of interconnect polygons. And the scientists looked at this and discovered that what this is probably due to is actually upwellings from the surface below, actually causing movement along the surface as much as several centimeters a year. So this planet is not dead by a long shot. And in fact, because of this upwelling of material from below, the surface has been resurfaced every 500,000 to 100 to 1 million years. That's a long time, but because of that, though, there's very little impact craters that are visible on the surface of Pluto because of this resurfacing. Also, you'll see these mountains, which are water ice that have that are literally floating in the nitrogen, because water is less dense than frozen nitrogen, water ice, that is. Water ice at this temperature is extremely hard, by the way. It's a long way from from the consistency of ice that we're familiar with. And the spectrographs on the spacecraft, I guess it's called LISA, showed that there are organic compounds on the planet, and there's methane, nitrogen, carbon monoxide, and water, as you might imagine. So there are there's quite a variety of interesting geology and on the planet. I'm going to talk a little bit about the question of life on Pluto, which seems preposterous when you think about the temperatures and all, but it's not as preposterous as you might imagine. When a scientist considers whether there could be life somewhere, you look at three basic requirements. One is there has to be some heat, some energy. There has to be organic molecules, and there has to be some liquid water. Well, it turns out Pluto does have a source of heat. It's radioactive decay, much like it occurs on Earth. And in fact, at one time, it was thought to be hot enough energy to possibly get close to melting some of the buried rocks. But in addition to that, we do know that there are organic compounds. So there's heat, there's organic compounds. Then the question is there any, and could there possibly be liquid water on this planet? And that seems rather unlikely, but there's evidence that there is. And one source of evidence is cracks, very significant cracks on the surface, indicating that if there was a buried layer underneath of water and it froze, as you know, water expands when it freezes. And so it's thought to very likely caused these large cracks. But in addition to that, there is Cryo Volcano. There's a Cryo Volcano called Wright Mons, which is quite high. It's about 150 kilometers wide and about 3 to 4 kilometers high, with a central depression of about 5 kilometers. What it means is, what a cryovolcano means, that this is possibly water coming from down below and coming up through the surface, much like magma occurs on the terrestrial planets like on Earth. And so instead of erupting magma, we're talking about erupting water. And this is the science, the analysis is, so what people think is going on actually in terms of the structure of the planet is there's an outer frozen layer and possibly a area of liquid water underneath that's responsible for the crack, these cryovolcano activity.
Mike, if I can just interrupt for a second, I know you'll answer questions at the end, but there's two that are hanging out there that I'd just like to get up. The first one goes back a couple of slides, and you may have just answered it, but what mechanism drives the upwelling that you talked about a few slides back?
Right, it's the same mechanism that drives the volcanic activity and volcanic activity on the Earth, which is heat. So the radioactive decay of elements produces heat, and that's what's causing the upwelling. Okay.
And the other is back on I think 2 slides back, why CO and not CO2?
I think there's CO2 as well.
Okay.
That particular chart just showed the CO, but I think there's CO2 as well.
Gotcha. Okay.
Yeah.
All right.
But carbon compounds, methane, CO, yes, absolutely. Okay, so then in addition to, so further evidence of water though. So we have 2 possible pieces of evidence having to do with the cryovolcano and the cracking, but there's no equatorial bulge on Pluto, which is a little unusual. Spinning objects often have, like the Earth does, it's wider at the equator. And one way this could have developed, that the bulge might have been collapsed if there was a subsurface ocean underneath and the ice shell not able to support and actually collapsing. So that's another little piece of data. It's a possibility. And then a third issue, or fourth issue, is that the heart-shaped object, it turns out that's above that object is where the moon Charon is located. And so it's tidally locked into that position. So it suggests that there's some extra mass below the surface there, and an extra mass could be a buried liquid ocean. So there are 4 pieces of indirect evidence that there might be water. And while none of them are conclusive, when you look at all 4 of them, it says it may be quite likely that there is liquid water underneath the surface. So the last question is, well, all right, so there might have been, well, how could liquid water survive at those temperatures? And there was a recent article in Nature Geoscience about this in May of 2019. And I'm not going to go through the whole article, but it dismisses some possibilities, such as presence of ammonia in salts. But it does come up with a suggestion that a insulating layer could have formed, and that insulating layer would be sufficient, even over 4 billion years, to keep a layer of water underneath in a liquid form. So, as unlikely as it seems, there could be life on Pluto. At least it has some of the basic ingredients necessary. So, while the outermost reaches of our solar system are not particularly welcoming by our standards, they aren't actually universally hostile. And so, in spite of the dark and the cold, there may be a possibility of some life underneath the surface. Okay, so we're going to now jump ahead to the extension of this mission, which occurred 3 years of additional flight by the spacecraft. And so here's the outer solar system again. Here's Pluto, and here's Ultima Thule. The name has a meaning of the most distant object at the border of the known world that has been studied by mankind. So that's kind of what it means. The goal of the mission, of this extension to the mission, was to learn something about what the processes that were going on in the early formation of our solar system. And what's interesting about the Kuiper belt is that what's happened out there happened, and it probably hasn't changed a lot in the 4 billion years since the solar system was formed. And so this is the object. It's called Ultima Thule. It has a more technical nomenclature to it, which I won't bore you with, but it's considered a CCKBO. So what does that mean? Well, cold classical Kuiper belt object. The larger object of the two is called Ultima. It's sort of it looks roundish, but it's actually fairly flat. It's 13 miles by 12 miles or so by 4 miles thick. So the dimension that we're not seeing is only 4 miles. The Thule, which is this smaller object up here, is less flat and is more round. It's about 8.5 or 8.7 miles by 8.7 and by 6.2 in the other dimension. And so it's actually much closer to being round. The overall object, the overall extent is about 22 miles along this longest axis. And we'll talk a little bit about how it might have formed here in a few slides. So this is a very interesting video. I'll talk for a second and I'll tell you what it is. It's a video that was taken by the New Horizons spacecraft as it was approaching. So the initial part of the video where you see, you see here is a very blurry version of the Ultima Thule, was taken from 310,000 miles away. And in 7 hours later, it was at 17,000 miles away, and you'll see the remarkable difference. You'll also see the rotation of it. You can see it's, I'll run it a couple of times. So you can see it rotates in this rather like a propeller, and not along its, you would think the most favorable axis. It's rotating on the axis perpendicular to the plane that we're looking at. But you can see how it comes into much sharper focus as it gets closer. The pixel resolution gets down from something like 8,000 feet per pixel to 420 feet per pixel at its closest. Also, the just a little bit more about the.
I want to create technology that makes global travel as safe as possible. I want to find new ways to manage waste and use more materials.
Yeah, someone is talking in the background. Yeah. Okay.
Okay, I think we're good.
Okay, the object has a rather long period around the sun. It takes almost 300 years, so significantly longer than Pluto does. But its orbit is almost nearly circular, interestingly enough. Okay, okay, so we're going to go on to the next chart. This is the highest resolution picture of the object. It was a composite of about 9 separate pictures that were put together by NASA. Its highest resolution is 110 feet per pixel. So it's pretty good. And we'll talk a little bit more about it. This chart shows the colors in the object here, which you can see here are mapped out, and they all are related to the reflectance of the object. So this is just a graph showing what the reflectance of the various, and the overall reflectance, I think the maximum is about 12%, and it drops down from there. The brightest reflectance at 12% are some objects in this depression on the Thule side, and also the joint in between the two. The red color that was in the previous pictures is a mix, is also these thiolins that I was talking about briefly, which is produced by UV light hitting methane and other compounds and producing this reddish color. This chart shows the surface morphology of the two objects. So the top one is the large one, the Ultima, and it has a variation across its distance of about 1 kilometer. And it's quite lumpy, as you can see. Thule is has only about a half a kilometer variation, except in that one crater depth is more than that. But overall, it's about a half a kilometer in variation thickness. There's a geomorphical map of the object, and I'm not going to go through all of this, but they have mapped the various features that are visible on the surface, and also the boundaries between them. Thule's main feature is this thing they call Maryland up here, which is a depression, most likely due to a meteor, some kind of an impact. It's 7 kilometers in distance across and 2 kilometers deep. So the average is about a half a kilometer variation, but this section of it is 2 kilometers deep. You have to pinch yourself to realize what amazing feat that observing this thing out at at almost getting close to 5 billion miles away, and we're looking at this in such a high resolution, which is pretty cool. This is a little more information about Ultima. It has it doesn't have any main features, but it has these little boundaries as it's shown here. And what these are thought of are the accretional subunits that probably were there first, and then these are boundaries between the various chunks that got eventually glued together to form the the object itself. And so these are just boundaries between these subunits. That there's also, except for this one impact, which probably is an impact, there's no other evidence of impact craters, and these boundaries are probably due to these boundaries between the chunks that were originally there that formed these objects. The lack of impacts is thought to be due to the fact that, for one thing, objects in the Kuiper belt aren't moving that fast. So the thinking is pretty much the shape that you're seeing here, with maybe the possible extension of this depression, is much like it was when it was first formed 4 billion years ago. And this thing is called a contact binary. That is, these two objects being bound together. And this is an attempt at just a quick explanation of how this might have formed. The thinking is there were these small objects, planetesimals or rocks of various sizes that were gravitationally in the same area and gradually coalesced. They slowed down as they were bumping into each other and eventually formed these two separate objects. And then eventually these two objects themselves merged together by their own self-gravity. The thinking is that this merging speed was probably very slow, maybe 2 meters a second, which is about the speed that you can walk. So it's just a very, very slow, gradual assembly. This is also thought to be very similar to the way comets are formed. If you know, you may know this, but most of the comets that we see in our solar system that come by, their origin is out in the Kuiper belt, and so like the Halley's comet is out in the Kuiper belt right now, and it's swinging. Then it'll be in quite a, I think 87. I think in 2087 is when it's expected to show up again. Anyway, the comets are formed much in the same way as we think that this object was formed. Okay, so because it was formed by self-gravity, that is, the objects gradually coming together and merging, the density is thought to be quite low, maybe as low as a third or so a gram per cubic centimeter, realizing water's density is 1 gram per cubic centimeter, so less than the density of water, so quite light. It was interesting, they did a few calculations and they thought that if the density was as high as 0.5 gram per cubic centimeter, which is actually the density of a lot of the comets, and it had a rotational speed of 12 hours or less, it would probably fly apart. And so its rotational speed is, I think I mentioned, if I didn't mention, I'll mention it now, it's about 17 hours. It orbits the sun with one side facing the sun all the time. And the solar irradiance doesn't change very much because the orbit is almost circular. The temperatures of the illuminated side may reach 60 K, or which is not very far above absolute zero. In the illuminated face, only the unilluminated face only reaches probably 30 K above absolute zero. That's pretty much the end of this section of the talk. The question you might ask, well, what's going to happen to the New Horizons spacecraft? And I told you where it was right now. It's currently about 4.8 billion miles from the Earth. That works out, by the way, and the astronomers are fond of using something called the astronomical unit, which is the distance from the Earth to the Sun. That's 93 million miles. So New Horizons is now 51 times that distance, or that Earth to Sun distance away from us. It's actually quite healthy. It's operating perfectly. I'm sure it's in a snooze mode at the moment, but it has enough power and fuel to operate for quite a while, and it might very well reach the boundary of interstellar space, where the Voyager spacecrafts are now. I was not able to find out what their plans are, what NASA's plans are for it, if they have any. It may be a serendipity thing, and it'll depend on what happens. But we don't know. You can't really see out much detail out there with our telescopes because they're so far away, and they're not like stars, so they're not illuminated. So I don't think there are targets out there that they've identified. But maybe something will come up. Okay, so we're going to now shift gears here and go to another spacecraft. This is a mission that is also completed, but in this case, the spacecraft is probably crashed into the asteroids it was studying. But Dawn is a spacecraft that is quite unique and that was designed to actually explore two asteroids in our asteroid belt. And it's the first spacecraft that was designed to do two. Now it turns out New Horizons has done two, but that wasn't part of its initial planning. And so it has taken 69,000 images. It did almost 2,500 orbits around the two asteroids. One was called Vesta, and the other one is Ceres. And it's actually traveled 3.5 billion miles since its launch, so very close to the actual distance out to Pluto. But it traveled that far because it had to first reach Vesta. I'll talk about this, and then it had to deorbit Vesta, and then catch up with Ceres, and then do the orbit around Ceres. So it has gone quite a distance in its lifetime. What's interesting about one of the interesting things about it is its engines. It does not use chemical engines. It uses ion thrusters, and they produce. I'll tell you a little about it in a second, but they produce a speed of the ions that are 7 to 10 times that of the chemical engines, but there's not that the actual amount of thrust is not very high because the effluence of the ions is low. For example, the engine that's powering that spacecraft, it would take 4 days to make a car accelerate from 0 to 60 miles an hour. So it's not a high thrust engine by any means, but when you add all the thrusting it did do over its entire life, it was actually fairly similar to the thrust that was produced by the Delta II rockets that put the Dawn satellite or spacecraft into space. And so ultimately it was a lot of thrusting. Why ion propulsion? It's not very powerful. The reason it is 10 times more efficient in terms of propulsion. So if they hadn't used ion propulsion, they would have had to use 10 times more propellant to accomplish this mission, which would have meant a much larger spacecraft and a dramatically larger launch vehicle. So this graph actually shows the difference between the efficiency, and what the efficiency is the amount of thrust produced per propellant, and the ion engine is way higher than, as you can see, this is a logarithmic scale up here in the 2000 range compared to like 300 for chemical engines, rocket engines, for example. So that was why they chose this, and it worked beautifully. And this is just a sketch of what's involved. There's a propellant supply, which is xenon, a source of energy, which is involved with getting the propellant into the engine, and then there's a voltage. There are voltage plates, electrodes that cause after the propellant is ionized, you have charged particles, and they're accelerated by the difference in potential between these two plates, and you get a beam that's thrusting. So, so getting back to the mission itself, the mission was to study two different asteroids that were very different from each other. So they're quite contrasting asteroids. Vesta, which was the first one it visited, is a dry, what's called differentiated object, which is very similar to the rocky bodies of the inner solar system, like Earth. And by differentiating, meaning it has multiple layers, just like Earth has multiple layers, and most of the bodies, the planets, the terrestrial planets, well. So Vesta was chosen because it has that feature. It's also closer, and it's closer to the Earth than the other. And the other is Ceres, which is a little further out. Ceres, by contrast, is much more similar to the icy moons of the outer system. So you have one asteroid that's similar to the inner solar system, and the other asteroid more similar to the outer solar system. And here's just shows you what happened with the what the sequence was for the mission. It was launched in September of 2007. It made several circles around the Earth, and then eventually caught up with Vesta on the 15th of July of 2011, a couple of years, well, 4 years later. And then it stayed there. It departed Vesta in September of 2012, and then arrived at Ceres in the spring of 2015, and it stayed there for several years before it finally ran out of fuel. So the mission, the purpose of the mission was to compare the difference in the evolutionary paths of formation of both, well, asteroids specifically, but also this knowledge about the planets themselves. How did the planets form? So by studying these two asteroids, we were hoping to learn something about how our planets were formed. Somewhat like the same idea as to why the Ultima Thule mission was extended, was to learn something about how things formed in the early solar system. And so here's a couple of pictures of well, picture of Vesta in Ceres. You can see Vesta is much smaller, and it has an irregular shape. Ceres is almost perfectly round. And I'll talk about that in a second. So this is a photo map of Vesta that was created from 10,000 separate images by the spacecraft while it was orbiting it from an altitude of about 130 miles. It has a diameter of about 330 miles, as I mentioned, a rotation period of about 5.3 hours, an orbital period around the sun of about 3.6 years, and a distance of about 2.4 times the Earth-Sun distance. And its temperature is a fairly frosty 306 degrees Fahrenheit below zero. Unlike most asteroids, it's thought that Vesta has several layers, and including a crust of cooled lava covering a rocky mantle and then a nickel iron core, somewhat similar to, say, what goes on in Mars. So as a result, Vesta is viewed as a protoplanet rather than an asteroid because it resembles the structure of the planets. And here's a closer up picture of the southern of the polar region, of which there's this massive. It doesn't really stand out in this picture that well, but there's a massive crater up here, which has a diameter about 95% of the size of the actual asteroid itself. Its crater is 19 kilometers deep and has a central peak that rises in the middle 23 kilometers above it. It makes it almost the highest mountain in the entire solar system, only tied by a mountain on Mars. This impact that occurred, which is estimated to have occurred about 1 billion years ago, excavated about 1% of the volume of the asteroid. In other words, it blew it away. And a lot of the material from this is responsible for a lot of other smaller asteroids that are in the asteroid belt, accounting to almost 6% of the main belt asteroids are thought to have come from this collision that cratered Vesta this much, as well as an entire group of meteorites. So now we'll move on to Ceres. So after the Dawn spacecraft left Vesta, it tied into Ceres, and so this is an image of Ceres. It's the largest object in this asteroid belt with a diameter of almost 600 miles. It's also considered a dwarf planet like Pluto is, but it's quite a bit smaller than Pluto. It's only 2.6 times smaller. It's the only object in the asteroid belt that is actually round, because the smaller objects don't have enough self-gravity to make the natural size of an object is a sphere, and if it's large enough, over time, an object will ultimately settle into a spherical shape. And Ceres is the actually smallest object that's in the solar system that has managed to become spherical. And things smaller than that have these irregular shapes. It has an orbital period of about 4.6 years and rotation of about 9 hours, and is a little further away than Vesta was, about 2 3/4 AU astronomical units from the Earth. It's thought also to have been have multiple layers, and it's as I mentioned, it's thought also to resemble a lot of the icy moons of the outer of the moons of Jupiter and Saturn. It has the density about 2.1 grams per cubic centimeter. So in other words, it's denser than water by almost twice the density of water, which means there's some rock in here too. And so it has an external layer of a crust, and then a layer of possible sort of slushy, salty water, and then the core is a mantle is probably hydrated rocks and ice. The thinking is that Ceres might actually consist of about 25% water, well, in various stages, frozen as well as possibly a slushy, salty liquid. It also constitutes about 1/3 of the total mass of the asteroid belt. So it's the largest object in the asteroid belt, and it dominates. It takes, and it has, as I say, 1/3 of the mass of all of the objects in the asteroid belt. This is one of the main features of it. It's called the Occator crater. It's one of its main features. It has a diameter of about 60 miles. And it's about 4 kilometers deep. It has this very interesting feature in the middle, which I'll show you in more detail in the next slide. This is a picture that the Dawn satellite took toward the ends of its life. It was orbiting at several hundred kilometers for most of the time it was there. But then as it was running out of fuel, they decided to have it get a lot closer. So it made some much more detailed images. For example, in this case, this is the very center of that crater, and it is taken from an altitude of 34 kilometers. And you can just see the amazing detail that's revealed in this image. Pretty impressive. And this is another close-up. The mission ended sometime in, I think, towards the end of 2018. But this is one of the last orbit that it had in June 16th of 2018, from about the same altitude of 33 kilometers. But this is the crater edge of that Occator crater that we saw earlier. A lot of amazing deal. This could easily be something that was taken on Earth in the Himalayas, for example. There's one mountain on Dawn, and it's right. It's shown here. It is about 5 kilometers high, and it's called Huna Mons. You'll look at the shape of it. I'll show you. It's estimated to be probably no more than several 100 million years old, because it doesn't. It seems to be a cryo volcano, and you might be interested to compare it to this thing. This is an object that's called a Pingo, Pingo. It's located in Canada, up in the Canadian Arctic, and it was formed by an upwelling of water from underneath, and causing it to essentially stretch the surface up into this interesting shape. And so you can see from the previous picture that there's some similarity to similarity to what we were seeing here to this. And it might be a very similar thing, except in this case it might have been the slushy water coming up from the middle and pushing up the crust to form this shape. So this is again one of the last pictures that was taken of the surface. It was although actually in this case it was still quite a ways up. It was 400 kilometers up. So but it is towards the on its last orbit before it crashed into the planet. And it did that because it had finally run out of fuel. And this crater here is about 75 miles in diameter. The next is actually going to be another video of the flyby of the spacecraft as it flew around the planet or the asteroid. So this is in false color. The colors are been changed just to make them stand out more carefully, so you can see the difference between the various elements, the salts and sulfates. You can see that crater as it goes by. Right there. Then there's another segment of the movie which is actually going to go right over the top of it. You'll see here in a few seconds. So there it is. That's the Okata crater coming into view right there. But pretty impressive technology to be able to do this sort of thing. Okay, so that's that. It was okay. So we're going to moving on to the last part of the talk. This is probably the shortest part, but it's a fascinating story. This is the Rosetta mission. The Rosetta mission it was a mission of the European Space Agency, the ESA. It was purpose was to actually orbit a comet and possibly drop a spacecraft on the surface of the comet. And actually it did that. So it's the very first mission that was designed to investigate a comet. And it was launched in 2004 from French Guiana. I'll show you shortly what the maneuvers it took, because catching up to a comet that was flying around at about 87,000 miles an hour is no mean feat. And so it's pretty impressive. It finally caught up to it in 2014, and it then orbited the comet for 17 months after that. And this is obviously an image of it, and you'll see that. This is what went on. The object, the launch was 2004, but then it made several flybys of Earth and Mars initially, and then it went into a flyby of the last flyby of Earth in 2009, and then moving out into a longer orbit in 2010, and then making a sweep around one more time, and then in 2014 catching up to the comet, and then actually in November of 2014, the lander, the Philae lander, was dropped onto the comet. So it made a lot of very complicated passages through the solar system to accomplish this. So this is an image of the comet. This is created by 4 separate images that were pulled together. And it was done on 31st of January in 2015. The object measures about 2.5 miles by 2.1 miles by 1.1 miles, and the overall, and the head itself is about 1.6 by 1.4 by 1.1. The density of the comet is about half the density of water, and similar to what we were talking about, or maybe about Ultima Thule. And porosity, it's about 60% air, and so it's not very dense at all. This is a 2-image mosaic showing an amazing scene on the surface of the comet, and it was done from a distance of about 20 kilometers above the comet. And I think the actual distance in this image is 3.1 kilometers left to right and 1.7 kilometers up above. And the resolution of the image is 1.7 meters per pixel. So amazing detail, which is really remarkable. This is the actual spacecraft. It's was about 9 feet by 7 feet by 7 feet, and central frame of aluminum, and it had this Philae lander also associated with it, and it carried the lander as well as about 360 pounds of instruments. One of the key takeaways from the mission was the measurement of the deuterium to hydrogen ratio. Deuterium is heavy hydrogen. It has an extra neutron. It has a neutron, and in addition to the proton and the nucleus, and so it makes it essentially twice as heavy as the normal hydrogen atoms. And so they measure the amount of deuterium to regular hydrogen on the comet, and it was about 3 times that higher than we find for regular water on Earth. So the conclusion is that comets, at least this comet in particular, but I think in more general, the feeling is that the water on Earth did not come from comets. That, in fact, in another talk which I've given, it's thought that probably a significant fraction of the water might have been formed originally during the formation of our planet, and originally in hydrated form, and then eventually being released, as well as being contributed to by asteroids. Asteroids have a deuterium to hydrogen ratio that's much closer to that of the water that we have on Earth. And so this is an image that I think shows the lander, the Philae lander, when it was brought down, but it wasn't really successful. It was intended to do measurements of various compounds, and it did do some of them, and it did achieve measurements of and determined that there were various compounds, hydrocarbon compounds, acetamide, acetone, methyl isocyanide, and this other one I'm not going to pronounce. But what happened was it unfortunately fell down, it bounced around because of the low gravity of the comet, and it got into a crevice, and which shielded it from the sun, so it wasn't able to get its batteries recharged, and so it really was not able to fulfill its ultimate mission. But it did do some of the measurement early on. It did some measurements and determined what some of the makeup of the comet was. But quite a feat when you think about the fact that this comet was moving at 84,000 miles an hour, to have a spacecraft first orbit it and then drop a lander like this onto the object. Pretty incredible. And this is the one of the last images that was taken in 2016 during, but again, showing some of the close-up detail from 16 kilometers away. So that's the end of the talk. I was going to briefly show some pictures that I have. Now I can't say I've taken this picture, but this is just just for an interesting. You might be interested in this. This is some of the others. Another space mission. This comes from the Juno satellite spacecraft that is orbiting Jupiter, and what was unusual. This was a very unusual mission that the spacecraft is actually orbiting over the poles. And so for the very first time, we saw what the polar region of Jupiter looks like. And this is an image that I made from the raw data. The Juno cam, which is a small camera on the side of this, was made, the images were made available in raw form to anyone who wants to get them. They're on the web. And so I, among lots of others, grabbed these images and I assembled the images into make this image of the South Pole, of which it has these various patterns of cyclones. And this is the very first time anyone has seen the South Pole of Jupiter. And it was taken, the field of view is sufficiently small, so it took 4 separate flybys of, or 3 separate flybys of the planet, because each flyby is not exactly goes over the same section. So by combining the image from 3 separate flybys, we were able to assemble a single image of the entire South Pole. And then there's another image. This one was much harder to do, and it shows a profile. You can see the South Pole at the bottom, the great red spot. This was done in a single flyby, but the interesting thing about the Juno spacecraft is that it has a very oblong elliptical orbit. It gets within 3,000 miles of the surface near the equator, and it goes out to 60,000 miles. So there was 4 separate photographs taken at very different altitudes and distances from the planet, and they all had to be scaled and squeezed and smushed and all to form because they're all taken at different distances. And so it was quite a challenge. But this is one of the maybe the most detailed image of Jupiter ever, even more detailed than we see from Hubble, because Hubble, after all, is quite a ways away. So this is not a very high resolution camera. It's only about 2,500 pixels on the side, but it has the feature that it's very close. And so you can, we were able to see these amazing images. And so this was another image that I made. And this is one of the images of the 4 that made that previous picture. But you can see the great red spot in great detail here. And these are some images I've taken of the moon with my 12-inch telescope. This involved 500 separate frames taken and then assembled, stacked together. And by doing that, what you do is you make an image with very good signal to noise, but you also deal with another issue with the moon, because you're looking through our atmosphere, and by having 500 separate frames, the blurring by our atmosphere sort of cancels out. The thing that stays the same in all 500 frames is the detail on the planet or the moon, whereas the blurring varies. And so when you stack 500, it kind of cancels out. So you can see the resolution of this, the Tycho crater, and you can, if you zoom in more, you can see an awful lot of additional detail. And I did some signal processing with something called the Wiener filter to do that. And this is just one of my galaxy pictures. This is taken with my 20-inch telescope of something called the Fireworks Galaxy. And I think I'll end the talk right here.
Well, Mike, you made a statement earlier about the feat of landing something at 84,000 miles an hour, the Philae lander on that. And at the risk of alienating any of my sports friends, it's really remarkable to think about what precision is enacted there, and then watching a game when Tom Brady can't hit a receiver at 25 yards away. It's kind of striking.
1,000 miles an hour. You're right. It is remarkable. I mean,
those
think the technical feats that these various missions that I went over. Just think about the technical feats there of all of this. It just totally blows my mind. The whole New Horizons and the Dawn mission, and then this one, the Rosetta mission, was just mind-boggling. As
impressive as the images of Pluto are, seeing those close-up landscapes on a comet is just unbelievable.
It is. It is, isn't it? Yeah, I totally agree with you. It's just incredible.
So we've got a couple of minutes for some questions if anybody's out there and wants to ask anything before we shut down for the night. I appreciate you coming tonight. If you'd like to unmute yourself, please feel free to chime in. Gary says, not just precision, but the fact that they're doing it at a time delay so far for corrections. That's right. It's not like steering a car where you turn the wheel and it goes left.
Yeah, these are, I think, what is it, 15 minutes to Mars, but then Pluto is 7 hours of to get a signal out at the speed of light to do any adjustment. And of course, this comet was quite a ways away too, so any adjustments there are certainly many. I don't know how many minutes to that but it was orbiting. The comet was moving all the time, very fast while all this was happening. So the distance to the Earth was changing dramatically on a continuous basis. So
imagine having to wait 7 hours if you're trying to teach your kids how to drive, waiting that delay to tell them to,
do this now. Yes. Yeah. 7 hours later, the message gets there. Yeah.
Sometimes with the kids, it feels that way anyway.
Yeah. Yeah, it takes a while to sink in is the problem. Yeah.
Yeah. So that was really impressive, Mike. I appreciate you coming and doing that. I especially knowing how busy you've been this week alone. Great.
Well, I enjoy doing it, and I think these missions are probably missions that most people. I think everybody sort of knew about the Pluto mission, but these other ones are a little less known to people. But I think they're very interesting and very impressive.
Mm-hmm.
And, that's why I thought this combination of things in the talk would be of interest.
Yeah. Hey, folks, don't be shy. I see some of you posting questions in the chat, which is fine, but I'd like to hear your questions in your own voices. So feel free to unmute.
I have a question then.
Yeah, Peter.
Oh, yeah. Well, I typed it in there, but I was just curious when it was a great talk. Thanks a lot. I just wanted to thank you for that. Really enjoyed it. So when this this Rosetta is flying around the comet, is it actually in orbit, like under the influence of the gravity of the comet, or is it just sort of like flying next to it?
No, it's in orbit. It was in orbit around that comet. Yeah.
Interesting.
Yeah.
So
And you can think about it. Comet is pretty small, not very heavy, very light.
Mostly air, right?
Yeah, it's air. No, it orbited. For 17 months it orbited.
Yeah.
Dr. Adler, I have a question about propulsion. You talked about the Dawn spacecraft and the ion propulsion. I think that's really neat, but I have to ask, is there a way to move in space other than by essentially hurling material out of one end of the spacecraft?
Not that I'm aware of. Anybody else have? Yeah.
Is there? Can you do like when a solar wind hits your sail? Have they talked about that? So that's like
that's true.
Action reaction thing.
Yeah. Well, solar wind does transmit momentum and light, and both solar particles as well as the actual light itself, light pressure itself attracts. So so the answer to the question is, you're right, absolutely. So I shouldn't have said that. What I said, that was a wrong answer. There are other means, and solar wind is one. A lot of features, a lot of nebulas, if you'll notice, sometimes have holes in the middle of them. And the reason is the solar wind from the stars that are in that nebula have actually moved the gaseous particles out. And so, yes, there are other means. And, if we can find ways of harnessing some of this would be a very low energy budget way of you're not going to move that fast, but and of course, with no resistance, no air resistance, that's part of the secret of the ion engine. It's that there's no resistance. And so a small amount of propulsion actually gets you over time a lot of effect.
Isn't NASA going to be launching a satellite soon that's going to try to bump into and change the orbit of an asteroid?
Wow, I'm not aware of that. Does anyone else have any information on that?
No, sounds very science fiction like, but if that's actually happening, that's fascinating.
Yeah, well, it has this feature, you know, there was a movie, right, you know, of an asteroid that was in danger of hitting the Earth. And
That's right.
so what do you do about it? Well, launch something to try to change its orbit. Yeah,
They grabbed the
anyway.
keys to the space shuttle, started it up, and headed out.
Yeah.
Robert, if you find anything more about that, I'd love to know about that.
Yeah, well, the big mission that, of course, I think most people are aware of is the Webb launch, which is supposed to happen this November. So we'll all be very interested to see that, because that's the successor to the Hubble, and it's much bigger. I think Hubble is a 2-meter telescope, and this is like 15 meters, and it's just huge.
I want to mention before we leave for the night, our next talk is a month away, November. It's David Aguilar, and he'll answer the question, just what is a planet? He's got a new book coming out, and he'll be doing that for us on November 4th.
Yeah, it's interesting. I was just sent an image of image that was taken by the very large telescope in Chile of a star, an extrasolar star, which actually has been masked to reveal 2 planets that are imaged next to the star. First time it's ever been done, actually imaging. We have all these missions that detected the planets, but this is actually a optical image of a star and it's in 2 of its planets. That's
Wow,
really remarkable. Yeah,
that's amazing.
Yeah, maybe I'll send it to you, Seth. You'd probably be interested in it.
Yeah, no, that'd be great. Thank you.
Yeah.
Dr. Adler, if I may ask another question, this one about Pluto.
Yeah.
I noticed you had an image of sort of the locations of the Kuiper belt objects, and they all seem to be kind of a circular orbit. But then Pluto's in amongst them, but it's all off kilter. Why is Pluto's orbit so not on the same plane?
Yeah, well, in fact, a lot of the objects are like that in the Kuiper belt. Pluto is not the only one. The Kuiper belt has much less overall organization than the inner planets. Although what's interesting is that Ultima Thule almost had a perfectly circular orbit, but the planes of the orbits are also are not in a constant plane. And that may be another argument as to what demoted Pluto from its status as one of our planets, because its orbit is definitely skewed and as well as very irregular. Yeah, one question that actually I gave this talk in the past, and then someone one question is no one's asked it here, but it's actually a pretty good question, is how do people figure out what these profiles are of these layers in these, like in Pluto? So they don't have like on the Mars missions, for example, the satellites orbiting Mars, several of them have radar, and there's now a lander, the InSight lander on Mars, that has sonar. I mean, that can actually directly probing the surface. And the same thing that Juno had capability of radar in probing Jupiter. So we actually learned a lot about the structure of Jupiter directly through direct measurement. But okay, so how do we determine that these layers exist in these various planets? And so she was a woman asked this question. I said it was a very good question, and I had to think about it for a while. And in fact, it was after the talk that I sort of gave it some more thought. But part of it is first you try to determine the density, because like the Dawn and the New Horizons never didn't have instruments that would have any radar. So there's no direct probing of the planets of Jupiter. Of Pluto or the asteroids. So, but what they do is that by deconstructing some information, like in Pluto's case, it has a moon, and so knowing the size and knowing the orbital dynamics of the moon, you can determine density, and so that's part of. So that's the first piece of information, and then you look at the surface and see what's going on the surface. For example, cryo volcanoes and cracks and things of that nature give you a clue that there's something going on below the surface. And then of course, the normal formation, and you can just look at Earth, because we can study Earth fairly well. And you have the situation where the center is often the place, because when these things were hot and molten at one time, the heaviest elements migrated to the center. And so by putting all these pieces together, this is how these profiles that are inferred about these objects, these planets and moons and what have you, without any direct measurement of them from the surface. Anyway, I thought that was an interesting question, and there's a question I asked myself, and then so my answer, I think it's reasonably correct after a little bit of thought.
All right. Well, if there's nothing else, Mike, thank you so much for this tonight. Really impressive. I enjoyed it, and I can see that everybody else did as well. So thank you for that. And thank you for everybody for coming tonight. We'll continue our series through the end of this year, and we'll start up our Orion series of talks in January. But next, stay tuned for November 4th with David Aguilar, What is a Planet? Thanks for coming, everybody, and thank you so much, Mike.
Sure enough. Thank you, and
All right.
I'll say good night.
All right. Good night.